All right, hello linear algebra students. I'm going to go ahead and record this lesson here and post it to YouTube for your viewing pleasure sometime this week. In class tomorrow, we will go over any homework questions that you have and maybe even do a little bit more notes. I don't know. We'll see what we have time for. I'd like to try to get through as much as we can. But just real quick, let's refresh our memory of what we learned last time. We were introduced to vector spaces. Vector spaces are just sets of objects, and we call those objects vectors that obey these 10 properties. We talked about what a subspace is, and we use this little notation. This is a subset notation. We use a little less than or equal to for the subspace notation. And yep, here it is on the next page. Subspace down here. This is the subspace notation. And there are three requirements to be a subspace. You have to contain the zero vector. You have to have the closure under addition, and you have to have closure under scalar multiplication. We did a little proof there. And we showed that the span of a set of vectors is always a subspace of the vector space that those vectors originate from. What else did we show? We connected some of this back to matrices. At first sight, it didn't really look like it was going to connect back to matrices, but then once we start talking about the span of vectors, then we realize, wow, it's really just a matrix. And by row reducing the matrix, you can see if the vectors are linearly independent. If they're linearly independent, then they create a spanning set. And the space that they span is a subspace of the overarching space. Let's see here. Well, let's go ahead and get started on the next section, which is on null spaces, column spaces, and linear transformation. So what is a null space? Null space, null usually means like empty, or it's another way to think of it is the things that point to nothing. And in this case, that's the way that we're going to be using it. So we have here a matrix A, and the null of A is a subspace of, well, we'll see, a subspace of Rn. And it's all x's, so that A multiplied by x is the zero vector. So it's basically, if this is a map, if the matrix A is a mapping or a transformation, it maps, it's all, the null space is all the x's that map to the zero vector. So here in this theorem here, it says, I don't know if I want to take the time to prove this. I think we will. I haven't looked over the proof, so let's see if I can do it cold here. Usually that gets me in trouble. The null space of an m by n matrix A is a subspace of Rn. Equivalently, the set of all solutions Ax equals 0 of m homogeneous linear equations and n unknowns is a subspace of Rn. Let's see. So let's see, how do we, in order to show subspace, what we need to do is we need to show three things. We need to show that it contains the zero vector. So how are you inside the null space? So null A, let's just write this down to start, is equal, oops, 1L. Null is written with two L's, but when we're talking about the space, it's just 1L. So null A is equal to, I'm just writing the above here, is the set of all vectors x such that Ax equals 0. Okay, so we want to show, one, that the zero vector is in this space. So A times the zero vector is the zero vector. Every matrix times the zero vector is a zero vector. So this implies that the zero vector is inside null A. All right, that's the first thing to be a subspace. Two, we need to take two things out of the null space. So let's grab them. We'll just choose two arbitrary elements. We'll call them x1 and x2 inside the null space. Then let's add them together. So then A times the sum of those two remember, we're trying to show closure under addition, which means that if you add them, they should stay inside the space. So what are we hoping that this is equal to? Well, we're hoping that this is equal to the 0 vector. Well, we can distribute the matrix by our properties of matrix multiplication. So this is going to be ax1 plus ax2. And this is 0 plus 0, which is 0. And this is because we'll say since x1 and x2, this is x2, are in null A. Okay, so this is closure under addition. The last one is to show closure under scalar multiplication. So x1 is in null A. To be fully proper, some people don't like to reuse. Well, I should say that it's improper to just reuse what you've stated in the previous part. You have to treat part 3 like a completely new proof. So each one of these are like standalone proofs. I'm not going to reuse x1 and x2 from part 2. Their purpose has been served and they're done. So now I'm reinitiating a proof. So I'm saying let x1 be in null A, and we're starting over here. And my goal here is to show that for C scalar, A times C x1 is equal to CA x1. And since x1 is in null A, this is just the 0 vector. So remember, being in the null space means that the matrix A maps you to 0. So then this is just the 0 vector, and we're closed under scalar multiplication. So this implies that null A is a subspace of Rm. We want M here because this this 0, I think I want N. It's easy to get that mixed up. We want N. We'll put a little box here, show that our proof's over. Why do we want N? Well, remember, this is A is an M by N matrix, and X is an N by 1 vector, equals 0 is an M by 1 0 vector. So this vector X, the null space is a collection of all these X's. So all those X's live inside of Rn. There we go. That proof took a little bit longer than I want to do. It's a short proof, but it's good for us to look at it. Let's keep going. Let's see if anybody's online watching the video. Nope, it's just me. That's sad. That's okay. You guys can watch this on YouTube. Okay. All right, so the column space of A, what is that? We write it COLA, column A, is the set of all linear combinations of the columns. So it's just a span of the columns of the matrix. That's called the column space of the matrix A. So we have the null space and the column space. And the column space isn't, let's see, the column space, this is the next theorem of an M by N matrix, is a subspace of Rm. And this is kind of a trivial proof right here. We showed this from the previous section. Let's see, where was it? Our proof was right. Nope. Where is it? Here it is. The span. Where is the span? Oh, here it is. So example 7, show that H is a subspace of V, so the span of vectors is always a subspace of the overarching space that they come from. So this is example 7. So what we could say here, whoops, got a little too far. So what we could say is by example 7, column A is a subspace of Rm. So col A is just a span of a set of vectors. So I should say 4.1, example 7, is, so then we get the column space as a subspace of Rm. Okay. Now this is a little different than the null space. It's a different size. Notice that the null space is in Rn, column space is in Rm. So if T is a transformation defined by x going from x to ax, so A would be the standard matrix for the transformation, then X would live in, the null space would live in the domain, where the column space doesn't live in the domain, but rather it lives in the range of the transformation, or you could say the codomain. Okay, so let's see. What's this next note say? Column space of an m by n matrix is all of Rm if and only if. So here's an if and only if the equation Ax equal b has a solution for each b in M. So this is equivalent to saying that the span of the columns is all of Rm, which is pretty trivial since the column space is the span of the columns. Good. Okay. Let's see, what does this say here? A linear transformation T from vector space to vector space. So here we're talking about, this seems a little awkward, but we're talking now about transformations not mapping from vectors to vectors, but vector spaces to vector spaces. So it is still taking vectors to vectors, but their codomains and domains are vector spaces. So instead of just sets of vectors or Rn or Rm, we're now actually talking about a specific vector space. Now, this is a little bit more abstract because you could be mapping from a very concrete vector space, say something like Rn, and you're mapping to something a little bit more abstract, maybe like a set of all polynomials, so Pn, P sub n. So that was the set of polynomials, if you recall, of degree n. So this is a little bit more of an abstract mapping, which before our transformations only take vectors to vectors. Now you could be taking vectors to polynomials, which we like abstraction like that because we can use it in more cases. So here we're just defining what a transformation between vector spaces actually is. And here we have linearity. This is, remember, a linear transformation. So linearity is if you take the transformation of the sum of two elements from the domain, then it gives you the sum of the elements in the codomain, or in the range. And here, if you take the transformation of a scalar multiple of one of the domain elements, then it just gives you the scalar multiple of the range element. So of what its image underneath that transformation. So the kernel, what is that? It's really just the null space of this transformation. So the kernel is just a set of all u's so that t of u is 0, the 0 vector inside the range space. And the range of T is a set of all vectors that are formed. Now this is this is the same as what we would have expected before, except the codomain is now a space. So the codomain is just a set, or a set of vectors, W, that happens to be a vector space. Okay, I think we should get to some examples now. So let's go ahead and start here with example 1. So we've got A is a 2 by 3 matrix, and U here is a 3 by 1. It says determine if U belongs to the null space of A. So let's go ahead and take their product and see if it's 0. If it's 0, then yes, it's in the null space. I don't have anybody to check my mathematics here, so if I make a mistake, you can shout at YouTube. But let me just double check my minuses. Okay, so here the first element, we're going to get an element that's 2 by 1. This is a 2 by 3, and this is a 3 by 1. So it's going to give us a 2 by 1. The first element is going to be 5 minus 9 is negative 4 plus 4 is 0. The next one is negative 25 plus 27 is negative 2, and plus 2, oh, positive 2. Is it positive 2? Yes. Positive 2, and then negative 2 is 0. Okay, so then the answer is yes. U is in null A. Yeah, cool. Next one. H is a set of all vectors of R4 whose coordinates satisfy this equation. All right. Well, and this equation. So it satisfies both of these equations simultaneously. Show that H is a subspace of R4. This is going to take a little bit of cleverness. So let's just say A minus 2B plus 5C equal. We'll subtract the D over. And then let's order these here. Minus A, minus B, minus C. Oops, I forgot my C here. And then 0 D's, so plus 0 D's equals 0. So I just moved the elements to the other side of the equation. And now what I'm going to do is I'm going to express this system of equations as a product of a matrix, coefficient matrix, and a vector. We've done all that matrix work we haven't done it for no reason. So here we're going to make good on all of our work that we've done. So this should give me the 0 vector, 0, 0. Okay, well, this is equal to, so this is, let's see, how do I want to say this? So the vector, we can call it the vector x is a, b, c, d. Is null of our matrix down here. This is, we'll call this A. So is null A. And the null space is always a subspace. It says show that it's a subspace of R4, so null A, which is a subspace of R4. Now this is always true, so always true. And that's, we could even go back to our theorem to show that, and that's this theorem 421. So we can say by theorem 421. Yeah, so it doesn't matter if these columns are linearly independent or anything like that. What really matters is that it contains the 0 vector. So the null space contains the 0 vector. It also has to contain or has to be closed under addition and scalar multiplication, which is what we have shown here already in this example. The null space is always a subspace. So that's what we're seeing here in example 2. I think that's all they wanted us to realize. So it's a little bit of cleverness to get to the coefficient matrix to realize that it's just a matrix equation. And then once you've realized it's a matrix equation, you realize that the set of solutions is really just the null space of that matrix. Okay, it says find spanning set for the null space of this matrix. Ooh, okay. We may have to use a calculator here, or you can just bear with me while I row reduce. You know what I'll do is I'll just pause the video and row reduce so you guys don't have to watch it. So I'll do that right now. Okay, here it is. I hope I've done it properly. I didn't do it on a calculator, I did by hand. So let's go ahead and find the null space. Now, I've just row reduced it. And so we want to find all the vectors that are the solution to the homogeneous equation. So remember what the homogeneous equation is. Uh-oh, lost my ink there. There it is. Let's minimize that. Check recording. Yeah. So AX equals 0. Remember, this is called the homogeneous equation. So the solution to the homogeneous equation are also, well, we could say those solutions are the null space, or they make up the null space. So here we have a vector x equals 0, just like that. Or you could start finding the general solution the way that we found it in chapter 1. So here, we have free variables. X1 is made up of here 2x2. It's made up of, this is also a free variable, which is x4, so that's 1x4, and negative 3x5. x2 is free. X3 is a basic variable. It's going to be made up of negative 2x4 and plus 2x5. x4 is free, and x5 is free. Okay, so now a general vector, solution vector, looks like this. x1, x2, x3, x4. Whoops, x3, x4, x5. Okay, and now we want to break that up according to what we've just found here, 2x2 plus x4 minus 3x5, x2, x, oops, so we need a negative 2x4 plus 2x5, and then x4, x5. Okay, so now we want to break this up into its parts. So we have a vector. This is the x2 vector. We have 2, 1, 0, 0, 0. This makes up x2. What makes up x4? That's the next free variable, is 1, 0, negative 2, 1, 0. That's x4. And then x5 is negative 3, 0, 2, 0, 1. Okay. So now these three vectors make up the null space. So we can say, says find the spanning set. So null of A, the null space of A, is the span of these solution vectors. So the solution always looks like a multiple of these three vectors. So the nice thing about linear algebra here is, what did we just do? We just did the same thing we did in chapter 1. We just slapped a new face on it and called it the null space. we found spanning sets for the solution before. That was back in chapter 1 when we were writing the general solution. And so now here we're just saying, hey, the null space is that span. So the next example, example 4, says find a matrix A such that W is the column space, where W is this a set of vectors here. And so we have to find a matrix that A, so that this is its column space. Well, let's partition it. So W, let's just continue this equals down. So let's just continue it downward here like this. And we'll say is the set, let's break it up, partition it with 6, 1, negative 7, and we'll put A, just like we did above. And then now let's break it up according to B. So negative 1, 1, 0. B, so that A and B are real numbers. Sure. Okay. And so then we could even go further. We could say this is going to be the set of the matrix 6, 1, negative 7, negative 1, 1, 0 times AB. So that AB is in the real numbers. Okay, so now then this is, you could also say that this is just the span of these two vectors, 6, 1, negative 7. And negative 1, 1, 0. Okay, so what is the matrix A? So A, if this is the column space, then we just slap those two vectors down as the columns. I mean, now, I did a lot more work than I perhaps needed to, of course. You could just read the coefficients of this and just slap it into a matrix and you've got your answer. But I wanted you to make these connections here, going down to each one, where it's all three mean the same thing. Okay. Let's see, example 5. If the column space of A is a subspace of Rk, what is K? Sure, I love this problem because I struggle with it. It makes me think about it every year. So here we want column A, so this is part A, column space of A. If Rk, what is Rk? So this is a 3 by 4 matrix. And so we have to think about the column space. So the column space is made up of a set of all columns of A. So if the column space is a subspace of Rk, well, what size are the vectors of A here? Well, they're R3. So this is a subspace of R3. They're 3 by 1 vectors. So columns of A are size 3. So here, what about the null space? You could probably just guess now that you know what the column space is always the size of each of the columns, so the null space is the size of a row. So then it's you could say, I think I won't write out the definition here. I'll just say the size of rows. So R4. Excuse me. Okay. So this is subspace. Okay. Yeah. So that's the size of its rows. Now, why does the null space have to be that size? Well, remember, it's A, the definition's AX equals 0, and so it has to be compatible for X has to be compatible for multiplication. A is a 3 by 4, so X has to be a 4 by 1. Oops, let's do a product. 4 by 1. And so that's going to give me a 3 by 1. So that has to be compatible. So all the x's here have to be a 4 by 1 size, which means they have to come from R4. Yeah, good. Next example. It says with A from example 5, find a non-zero vector in column A and a non-zero vector in null A. That's easy enough. Now, the mistake here would be to choose one of the columns for column A and to choose one of the rows for null A. That's not quite right. It's right with a column. So we could say this column, the first column, is in column A. But you can't just take the first row in null A. So we're looking for a vector x so that when I multiply it to A, it gives me 0. Remember, we're looking for a vector in the null space. Now, in order to find that, we're going to have to row reduce. So I'm going to pause the video again and row reduce. You can do it on your own. And then here in a minute, we'll look and find a vector from the null space. Okay, that took me a little too long. I ended up using a calculator. But I've got it here. So here's our row-reduced matrix, and we're looking for a vector x1, x2, x3, x4. That gives me the 0 vector, 3 by 1. Okay, and so then that's basically just the general solution. So we're looking for x. So x1 and x2 are basic variables. x3 is a free variable. x4 is a basic variable. So we want x1 in terms of x3. So x1 equals negative 9x3. x2 is 5x3. x3 is free. And x4 is 0. Okay, so this implies that the spanning set for the null space, so we'll just say null A equals the span of, let's see, -9, 5, 1, and 0. Just this one vector. So all the solutions of the homogeneous equation look like this vector. They're multiples of that one vector. Great. Okay, example 7. With A as from example 5, so 2 examples ago, and example 5 was from example 6 as well. reusing some of the matrices here. Let U be this vector and V be that vector. Determine if U is in null A, could U be in column A? And determine if V is in column A, could it be in null A? Well, let's see. So U is this vector right here, and they want to know, is it in null A? Well, null A looks like this right here. So all the vectors of null look like null A look like this vector. So it's possible at first sight it could be in the null space because it's the right dimension. It's a 4 by 1, and null space is a subspace of R4. So it looks like a candidate. But once we look at this here, we could say C times U, let's just say CU. CU is not equal to negative 9510. So U is not in null A. Could it be in column A? Well, the column space of A is a subspace of R3. So subspace R3, there's no chance. U cannot be in column A, wrong dimension. Wrong size, or yeah, we could say wrong size, you could say wrong dimension. Well, let's see if we have more luck with part B here. Is V in column A? No, or well, here's V. Is V in column A? Now that one's going to take us some work. So in order to determine if V is in column A, we want to know, is it in the spanning set of the columns of A? So let's write down the columns down here. So here's the first column, 2, negative 2, 3, 4, negative 5, 7, negative 2, 7, negative 8, and then 1, 3, 6. And so we need to take multiples of each of these columns, A, B, C, D, and see if we're going to get 3, negative 1, 3. So is this a multiple of these 4 vectors? So how do we do that? Well, you've done this before. It's just the same question, just asked a different way. What we have to do is row reduce, and if the system is consistent, then we know that the vector is a multiple of those 3. Now, have we already done this work before? We don't really have to do any more. We've done this work once before, so I'm not going to go through it. Right here, we've done it. Let me use a different color. So we'll say underline those pivots. So we'll say 3 pivots, which if we take that down here, this implies that the column A, or the columns span R3. So the answer is yes. V is in column A. Then they ask, is V in null A? No, wrong dimension. So V is not in null A. V is in R3. V is in R3. Null A is a subspace of R4. So they're just the wrong size vectors. You can't be in the same space if you're the wrong size. All right, a couple last examples here about mappings between vector spaces. Example 8 here is a mapping in which you are familiar with. It says let V be the space of all real valued functions on an interval AB. So this is a very calculus-like proposition. So you've got some real function that's defined on the interval A to B. It's got to be defined, real valued function that's defined on the interval A to B, that's continuously differentiable. So continuously differentiable just means that you can take its derivative and its derivative is continuous, and that you can keep doing that again and again and again. So let W be all the spaces, be the space of all continuous functions. Okay, so W is a larger space. So V is restricted just to this small segment of the real line. And W is not restricted at all. It has functions defined for all real values. Then they say define D, so D is some mapping, a transformation from V, a function space V, to W. And it's defined by F going from F to F prime, in which um, this we call this, you maybe have heard this before, the derivative transformation. And yes, it's just the regular derivative. Is it linear? Okay, well, let's see here. So what does linear mean again? Let's go back. It has to have linearity or additivity and homogeneity. This is what we call additivity. So if you take the transformation of the sum of two elements from the domain, it's the same as the transformation of each of the elements in the domain, or the sum of the images, I guess, in the codomain. And then you have homogeneity, where if you multiply an element from the domain by a scalar, you can just pull that scalar out and multiply its image. So let's see, does the derivative transformation abide by those two rules? So if I have some function, now we're not adding the domain elements of the function, we're adding the function. So let's maybe say let f and g be two functions inside of v. V is the initial space defined on just the real segment. Okay, then f plus g, since this is a space, it's still in V. Um, so this is still in V, the sum of the two functions, because f was defined on the real segment, g is defined on the real segment. Adding two functions that are both defined on that same segment are still defined on that same segment. And so now let's take this mapping D of f plus g. Well, what does this mysterious D do? Well, it takes derivatives. So we want, the way we could say this is d dx. You could write it like that, f plus g, or you could just put a little prime. In fact, to be consistent with the notation that they used right here, I should probably just say f plus g and put a little prime up there. Now, what is the derivative of the sum of two functions? Well, we know that from calculus. That's just f prime plus g prime. That is the sum of the two elements from the codomain. So these are the two images. So d of f is just f prime, and d of g is just g prime. And so by taking d of f plus g, we get f prime plus g prime. So it's just the sum of the two images. Well, what about scalar multiples? So what if I have d of cf? Well, if this is some polynomial, you can just pull the constant out of the derivative. If this is cf prime, we know that the constant out in front of a derivative doesn't change the derivative itself. It's just going to be f prime. So this is cf prime, which is just c df. Yeah, so there we go. I probably should write this out. df plus dg. Bear with me as I cram this in here, and my writing is very poor. But yeah, so what did that achieve? So all of that work just shows here that D, the derivative transformation, which we've been doing since BC Calculus, or since pre-calc honors, the derivative transformation is linear. It's a linear transformation between two function spaces. Okay, well, let's look at the next example. Define a linear transformation T to be from all second-degree polynomials, so this would be quadratics, to R2. And this is the way that it's defined. T of P goes to P0, P0. Okay. Well, that's kind of uninteresting. What do they want me to do? Find polynomial P1 and P2 that span the kernel of T. and describe the range of t. Aha, they're using some fancy vocab here. So what is the kernel? Well, the kernel is like the null space of the transformation. So we want t of a polynomial p0, p. We're looking for all t of p that give me the 0 vector, 0, 0. Okay. So what does the transformation do? It just plugs in 0 into the polynomial is what it does. So what would that look like? All the polynomials that map to 0, 0, or that when you plug in 0 give you 0. A polynomial that when I plug in 0 gives me 0. Well, what that means is that there is no constant. So the polynomial p must look like at squared plus bt plus 0. So this is what the general polynomial must look like in order that it gives me the kernel. So trying to think of a more foolproof way without going into the next section here. Find polynomials p1 and p2 that span the kernel. Well, here it is, p1 and p2. Okay, so I think p1 is, we'll just say t squared, and p2 is a polynomial t. So this is all quadratic terms, and all linear terms. And if you add these two together, then they give you the kernel of this transformation t. And the kernel is really just a null space here. So this is just going to look like the kernel, we'll say k. I think it's KER is how it's abbreviated, or is it KE? Yeah, KER of t, the kernel of t, is just going to be the span of t squared and t. It's the way that you can think of it is you've got the domain space. So this domain space is all polynomials. Here's the range space, or the codomain, R2. And this is just all 2x1 vectors. And so what we want to do is we're looking for all the vectors here in P2 that map to the 0 vector in R2. So we're carving out this right here, what I've highlighted. Let's maybe highlight it properly. This right here is the kernel of T. So the kernel of T is really just that subset of the polynomial space that maps to the 0 vector in R2 according to this transformation. It's a pretty abstract idea. We're throwing out a lot of new terms there. Kernel, we're talking about range and transformations of polynomial spaces. I mean, it's quite abstract. But this is really the fundamentals of some of the things that are to come. So yeah, I think this is enough for tonight. So when you guys see me, if you have questions about really anything that you've been working on, that will be a time to work on it. I imagine you probably won't have questions about this yet. You might. But we'll just field some questions, maybe start on this section. I don't want to do that, really. I want to stick to the schedule that I came up with, but I mean, if you guys are okay with moving on, I guess we move on, but I'll just feel it out tomorrow or on Tuesday and see what you guys have to say. But thanks for watching, and I'll see you guys later.